here at CIMMYT for, I lost track of how many years, about 8 years it looks like.
Yep.
And has done a lot of wonderful things, which I will mention at the end of the seminar as we acknowledge her, because this is in many ways an exit seminar for Denise. She will be retiring at the end of this month, at least retiring from CIMMYT, and probably, in fact, I know she'll be doing other things professionally afterwards, but officially retiring. So it's a congratulatory moment for us. We're quite pleased and happy to see Denise. And I've put on the screen, you can hopefully see her professional experience, which I just find quite fascinating, starting with working with baboons in the Masai Mara, then going to Brazil, working in Manaus with World Wildlife Fund, then a Fulbright Fellow in Spain, before moving into still pretty remarkable, but perhaps more customary or more common types of activities in different parts of the United States in her studies. She did her work primarily in botany and in biology. As you can see here, she got her PhD from the University of Iowa, looking at ecology, and then she also did her bachelor's in biology. She spent, when we recruited her to CIMMYT, she was working with Ed Buckler at Cornell University in the famous anthill, where there's so much hub of activity in research, and so many productive researchers and research come from that laboratory where she was helping to coordinate and to ensure the efficiencies of that lab. So today we have Denise giving us an exit seminar. I've actually lost track of the exact title, but I'm sure it will be on your first slide. I'm going to stop sharing now so you can go ahead and put your presentation on the shared screen. But it's really a pleasure to welcome Denise to this seminar, and she'll be telling us, I'm sure, about some of her experience and insights in this role that she's had with us at CIMMYT for 8 years. So over to you. We will have time for questions at the end, so please either type your questions into the chat. That's probably the most efficient way, or be ready to ask them at the end of the seminar. So over to you, Denise.
Good morning, afternoon, and evening to everyone. Thank you so much for being here with me on this this interesting day. I'm going to. I hope everyone can see my screen and hear me.
Yes, we see and hear you well.
Yeah, I sort of picked a big title: the Plant Genetic Resources Network of the Future, Seed Security Underlies Food Security. So as Kevin mentioned, 8 years ago, I became the curator of the Maize collection at the CIMMYT Germplasm Bank. And I found out that I had a lot in common with Woody Allen. And what he said is, I have no idea what I'm doing, but incompetence has never prevented me from plunging in with enthusiasm. And if I'm anything, I'm enthusiastic. So I we'll go on with what we're going to talk about today. So what are we plunging into today? First, I'll do a little background on what I consider to be the big picture of the global network of plant genetic resources. And then I'm going to delve in deep into a story of a project that connects all of the players in this network. And then I'll go on to talk about what my objective was when I gave a talk in the Genetic Resources Program meeting 4 years ago. And my objective is to pass on a better bank to my successor. And I'll comment on whether I think I'm doing that. And then, of course, at the end, thanks to many people. So the goal is to have fully secure and accessible plant genetic resources for food and agriculture. And in this case, where there is the potential for a multilateral flow of both germplasm and knowledge among the participants. And who are those participants? Well, basically all human beings on the earth are involved ultimately in this endeavor. And this is a kind of a schematic of how I picture this. If you go to the upper left, you see the individual unit called a family seed reserve. And those are the precious seeds that a family will keep and use for their next crop and harvest. And in a connected system, those people in that family would back up their collection in their local community seed reserve. In turn, that community seed reserve would then be backing up its collection in a national or regional germplasm bank. Ultimately, these entities would be backing up their collections in an international germplasm bank, such as CIMMYT. And then CIMMYT backs up its collection to Svalbard, the germplasm bank in the North Pole, which is the ultimate backup for this kind of system. But really the reality in 2020 is those links between these different entities are mostly extremely weak, except for that link to the top between international germplasm banks and Svalbard. One of the goals of every international germplasm bank in our system, and there are 11 of us, is that we have at least 90% of our collection not only backed up in Svalbard, but also backed up in a second location. So this final link here is what I would consider extremely strong, and there's an incredible amount of investment of time and energy in that link. So today I'm not going to talk about that link. I'm going to leave it right there, and I'm going to talk about the rest of the system. And to do that, I'm going to talk about the story of a partnership that we developed, CIMMYT Maize Bank, with a project called the Buena Milpa and with the germplasm in Guatemala, ICTA, with an NGO called Asopuch, and with rural maize farmers. This system, what you see is we are trying in many different ways to really strengthen all the links between these institutions and ultimately to help rural maize farmers. Where are we working? We're working in the western highlands of Guatemala in an area called the Cuchumatanes Mountains, which is a beautiful place, but it is a place of a lot of poverty and malnutrition. And this project, Buena Milpa, was working in that area. And the scientists realized that there are other NGOs in this area, and they have developed a network of germplasm banks, community seed reserves, and they invited us in the CIMMYT Maize Bank to join them in this project. And for the first time, we went there in November 2015, so that's 5 years ago. And we visited the National Germplasm Bank, which is up there on the upper left. You might think it looks a bit on the rustic side, which it is. And then we visited community seed reserves. And even though I had always been interested in working with community seed reserves, this was my first real experience. And so we visited a number of them as part of that network. And also we participated in an agro-biodiversity fair where committees, the local committees from all of these community seed reserves come together and show their diversity and exchange seeds. So what was our starting point? The starting point is the traditional seed storage methods of local farmers are limiting the food security in an area greatly affected by malnutrition and poverty. Community seed reserves could provide a very effective way to improve seed security, offering a safe, accessible source of high quality and locally adapted seed for annual plantings and in emergencies, such as crop failure due to local weather conditions. So our questions that we were tasked with answering is, are the existing community seed reserves, or CSRs, in the Cuchumatanes living up to these expectations? And if not, how can we make them better? So in this region, as in many rural areas of the Americas, farmers have different methods for storing grain and seed, and we saw a number of those in corn cribs or trojes, or in metal silos, and they could be either still in the husks or shelled in sacks. And all of these have drawbacks. Community seed reserves can provide an alternative storage option for seed. And here you see actually a diversity collection of many different kinds of maize from this particular community. But one of the linchpins of the community seed reserve are the private accounts. And the way this works is that each farmer harvests his or her seed early in the year, and they have their grain, which is what they use for their own consumption. And if by chance they have leftover, they can sell it. But they always select out the seed that will be for the next planting. And what they do is take that seed to their local community seed reserve, put it in their, basically it's kind of like a bank account, put it in the flask with their name on it, and it stays there for about a year until the next year. And they come back, they take that seed, they plant it, and they repeat it. So that is the basics of one of the core functions of a community seed reserve. But they also provide other important services, such as many groups do participatory breeding and have improved seed, which they offer to their community members. Also, they have a silo that they use for emergency grain in case of a total disaster, which can happen every 5 years or so. They can have almost complete crop loss. And so that emergency grain can be used in those situations. But one thing that we observed in the community seed reserves, these little buildings are all equipped with hygrometers on the walls. And we started looking at those hygrometers, and we noticed that the humidity is very high inside, 88%. 59% was probably the lowest we saw, 82%. And even inside the flasks, you can see by the little indicator cards, which are very pink, and inside those flasks, the seed inside the flasks is also very wet. And why is this important? The longevity of seeds in storage is highly sensitive to both moisture content and temperature. Generally, the duration of seed viability is reduced by half for every 1% increase in moisture content. And that is pretty incredible. Or an increase in temperature of 6 degrees Celsius. So this is a very, very critical aspect of storage to look at. So this problem we noticed by visiting these seed reserves, and we decided that we needed to come up with an economical solution of lowering the humidity inside the seed containers and not the whole building. Remember, most of these community seed reserves do not have electricity. And so they can't just switch on the dehumidifier. And so it seemed to me like what we had to do is concentrate on lowering the humidity inside the seed containers. So after the first visits, I went back to the office and started searching for a good way, a low energy way to dry the seeds. And I found a nice little article online which described that India was opening its first low energy gene bank, which uses an innovative technique based on desiccants to dry vegetable seeds for storage, a technique that requires very little power to operate. So of course that really caught my eye. And what this was something called drying beads. In Spanish, we are calling them cuentas secadoras. And those are what those little balls up in the upper left corner there a special kind of clay called zeolite, and they absorb a good proportion of their own weight in water. So dry seeds are completely resistant to insect infestations. This is the important key factor here. And all around this new drying beads, the technology, a group of scientists developed something called the dry chain concept. And what that is make the seeds dry and then keep them dry. And you can see the website down there in the corner if you want to check this out. And we thought, well, it looks like something we should try. So I got in touch with a group at University of California, Davis, Kent Bradford and his group. And Kent decided that he was going to loan us Pedro. Pedro is Kent's right-hand man there at the Seed Biotechnology Lab. And he came down with us, and that was myself, Ariel Rivers, who at that time was working at CIMMYT in the Sustainable Intensification Program, and Pedro. And we visited, again, the community seed reserves. Now we're getting into 2016, as you can see. But we had a great trip. We got to visit many of the local committees and talk about what their problems are. And you can see here, Ariel's checking out some insects in the open flask. And Pedro down there is showing how drying beads work to a group of local ag techs. So we also needed a fast way, an expensive way to monitor the humidity. This is another important aspect of this kind of work. And already the UC Davis people were using this indicator paper, and you can see that it's very effective, giving you a signal as to whether the seed is wet or dry. And you can see that healthy seed is normally drier than the moldy seed on the right. And the Horticulture Innovation Lab, also at UC Davis, developed what's called a dry card. And it's like a little the size of a business card, and it has a strip of indicator paper, and it's very easy to identify if your seed is wet versus dry by looking at the color. And it's a very inexpensive piece of monitoring equipment. The other thing is we wanted a way to monitor the seed viability where everyone can see the results. And just so happened on one of our visits, we saw one of the farmers actually had built his own sand bench. And we were busy talking about how we could implement this very simple technology. And I also remembered back to my days in the very first Maize lab when I was a postdoc. And it was a lab where they were doing a lot of screening of mutants. And so they just had to grow the maize seed just for a few days to get the phenotype. And they used this little device called the sand bench hole puncher to create little small plots of 100 seeds. And you'll see that we ended up using this technology. And this one in the picture is actually the one I went back when I went back to Ithaca for home leave. I actually borrowed the sand bench hole puncher from my old lab and brought it back, and we built some new ones. So also, you know, all through this, we were giving workshops to people in Guatemala City and demonstrating sand bench testing, dry cards, and basically explaining the kind of the physiology behind the work that we're doing and what we're trying to do to help them keep dry seed. So we were very involved with a lot of outreach, but what we really wanted to do was to do an experiment that showed that the drying beads really were the method of choice. So we ordered quite a bit of equipment, and it came to us from Thailand, from Rhino Research and Johan van Asbroek, who works in Thailand. and developed the use of drying beads for drying plant material. So we've got drums, we've got boxes, we've got drying beads, and we're ready to get going. But we still needed a few more things to get our pilot experiments underway. We needed a source of dry cards, and we needed some seed to experiment with. And in February 2018, we got both. Rachel Cox, who was the first director of the Buena Milpa project, had left, started her own NGO, and she became the sole distributor of dry cards in Mexico and Guatemala, and still is to this day. And so now we had a source of dry cards, and we had them in English and in Spanish. And we did some of our own testing in the gene bank. And you can see that these little cards are very, very accurate in tracking the humidity. This is a series of maize seed that we've measured with our moisture reader, and we see that the dry cards are tracking right along with the different levels of humidity. So where did we get the seed from? Well, you know, we had other projects going. We have a project going in in Jala, and there the farmers wanted to start a community seed reserve. And at one of our meetings in Jala with them, they brought 13 coffee cans full of landrace seed, each one donated by different farmers to start their own community seed bank. And that's, you can see it sitting there on the table. However, when we pulled out our dry cards, which at this point we now carried with us everywhere, you can see that all this seed is not stored in a proper way. It's all very wet. So we borrowed that seed, brought it back to the bank, and one of our technicians, Cesar Sanchez, who's quite good at designing innovative solutions, what he did is he took the flasks that they actually use in Guatemala, are what you see on the left, are completely opaque plastic, and normally the lids are opaque and you cannot see inside. But what you want to be able to do is monitor without taking the top off. So Cesar installed a window in the lid, and that's what you see on the right. So now we had a very nice design that will allow us to monitor without having to take the tops off. Well, now or never. It was time to really get to work. And in March 2019, our new postdoc, who was a seed biologist, Filippo Guson, arrived at the lab. And somehow I managed to convince him that he really needed to go to Guatemala and study seed drying in community seed reserves. So now we have our man on the ground and we're ready to go. So here's what we did for the 2019 seed drying experiment. And these were the hypotheses that we're testing. 1, seed quality and viability are maintained better when the seed is dried with drying beads. 2, seed quality and viability are maintained better in hermetically sealed containers. 3, seed stored in a community seed reserve is maintained better than seed stored in a family seed reserve. So we needed a really good design, and that's what we came up with. Each experimental set would include the following. You can see in every reserve that we worked in 3 different communities. We had a data logger constantly taking data on humidity and temperature. And then we had a set of 9 treatments. What do they include? So one treatment, the one across the top, was a net bag. Of course, not hermetically sealed. That seed is basically exposed to the elements. And of course, no beads are involved. The second treatment was putting the seed in a plastic flask, which is hermetic, but no beads. So the seed was dried, put out on a patio, and then considered to be dry enough. So then the other container is a plastic flask that, yes, is hermetically sealed, and yes, has beads. And what you see here is a experimental set ready to go, ready to place in one of the 3 communities. Also, in each community, we had a community seed reserve and we had a family seed reserve. So we had the 2 types of reserves represented, 3 treatments and 3 reps of each treatment. And you can even see right there in the beginning, we're ready to go. The cards are blue down there where the seed has been dried. The cards are already pink where there's been no extra drying. And then of course the cards are pink where are exposed to the air. These 3 communities represent a range of different environments. Climentoro was at the highest altitude, almost 3,000 meters of altitude. Quilinco was slightly another 500 meters lower. And then San Francisco was a community that's more of a tropical kind of environment. And you can see by the mean temperatures and the relative humidities that these are different environments. So we had to build our own sand bench just to kind of get the hang of it. This is one we built at CIMMYT, right out there next to the bank. And you can see we've got the sand bench hole puncher in action, creating little 100 seed plots in the bank. And we're doing our first trial there, getting some practice. This is what building a sand bench in rural Guatemala looks like. This is what I'm calling the in situ look. And here are the 3 sand benches that were built one at each of the communities. The humidity monitoring was done in a couple of different ways. Here on the left, you see Filippo's downloading data from the data logger from that particular community seed reserve. And you can see we've got dry cards all around. And we do have also a portable humidity reader also. The other thing we did was keep track of grain quality. And so at each data collection point, and there were 2 at 3 months of storage and then at 6 months of storage, you can see everybody, the different teams are examining the seed and calculating the percent of intact seeds that had no insect or fungus damage. So there's 2 groups working on that. And now let's take a look at the data. Okay, so the way this is set up, Climentoro, remember, is up in the upper left corner is the high altitude location. Quilinco is a little bit lower. San Francisco is the lowest altitude of the 3. And what you see here is this is the data, only showing the data from the seed that was dried with beads and stored in hermetic flasks. And what you can see that they maintain high viability. On the y-axis is percent germination when we plant the seed in the sand bench. Okay, so you can see that in all 3 locations at all time points, the seed that's in hermetic flasks and dried by drying beans is all very high. Now let's take a look at the other treatments. Here's the case of what happens when you put not dried seed into a hermetic flask. You get some dramatic loss of viability, and you see that it's happening in all 3 communities. There was no significant difference between what was going on in the community seed reserves and what was going on in the family seed reserves, so the data were merged. Now we add in the final treatment, which is seed stored in net bags. And what you see is, yes, just like wet seed in flasks, it loses its viability over time in all 3 communities, but the degree and the pattern is different according to the environment. And the other thing that we were collecting data on was seed quality. This is the percent of intact seeds. And you can see that the seed quality also reflects temperature and humidity differences among the 3 environments. What happened in San Francisco is now we started getting differences between the family seed reserve and the community seed reserve, which were not significant in the other 2 environments. So let's take a look at the hypotheses and our results. In the first case, Seed quality and viability are maintained better when the seed is dried with drying beads. Yes, 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 always, in all environments, in all reserve types, it's improved by drying with drying beads. Seed quality and viability are maintained better in hermetically sealed containers. Only when the seed are properly dried first before conservation in a hermetically sealed container. And lastly, seed stored in community seed reserves is better obtained than seeds stored in a family seed reserve, but this is not necessarily true. It really depends more on the storage, the quality of the storage. Community seed reserves do show some technical advantages because they tend to have a lower and more stable temperature, and they also have more consistent pest control. So this is what we picture. This is how we picture using the dry chain and community seed reserves. Here you've got the harvest in the beginning of the year. You take your new seed to the store in the community seed reserve. At that point, the local committee will do a dry card test. If the seed is dry and blue, the indicator is blue, we're happy, and it goes directly into the flask. If it's not dry enough, it'll go into a drying drum. And what this is there are drying beads in this central core, and it acts as a kind of like a chamber. So you can use that, your drying drum or dry store, to dry down the seed. Once it's dry and you check it with your dry card, you can then put it into the family's seed flask. And finally, during the year, you do monitoring, which is very easy to do because you've got those cards in there and you can check at once a month and see, are they blue, are they pink? If they turn pink, they go back to the drying drum. If they're blue, they can go on. Before the next harvest, it's possible that you may want to check the seed viability before you plant it in the ground. And there you go. So this is our vision for how to use this dry chain technology in community seed reserves. So the beat goes on. There are ongoing and future experiments already happening in the Cuchumatanes. In the community seed reserve of Quilinco, the dry chain is being implemented, just as I showed you in the previous slide. But also, one of the technicians in Asakuch, Saira Tello, she will start a new experiment, and she's going to be comparing 3 different desiccants: silica gel, drying beads, and a locally manufactured kind of drying beads, plus 2 traditional methods of drying, charcoal and rice. And she's going to do this in one community. And just for the sake of dry bead folks, the ones on the left are locally manufactured in Guatemala by an NGO called Senacri. And they've never really truly been tested. So we're going to put them head to head with the drying beads, which you see on the right. So what about in germplasm banks and breeding programs? Can we apply dry chain technology? Well, why not? It's seed, it's grain. You can try using dry chain technologies. And so what we did is we decided to try it ourselves. In Agua Fria Station, which is CIMMYT's tropical station, there was an extremely old drying cabinet, which we fondly called the Green Monster. As you can see, it was bought in 1967. It was probably one of the first things they bought to equip this station when CIMMYT began. Can we convert the Green Monster into a low temperature seed dryer using beads? This was our challenge. Well, we did some rehab, and what you can see here's a nice makeover of that cabinet that you saw in the previous slide. And here's a diagram that shows what we did in each of these sort of cabinets, individual cabinets. We actually put mesh bags full of activated drying beads in the bottom, and then we put on the shelves maize, and we turn on the ventilator, which we had, of course, rehabbed. It was not working at the time we started, and we got the air flowing, and the air was flowing through drying beads, and that was drying the air, the forced air that was drying down the maize. So what is the problem we're trying to address? Well, it takes weeks for us to dry our freshly harvested seed using unheated forced air in our drying room at our headquarters bank. And we do this because drying with heat is considered to be detrimental to the long-term viability of seed. And of course, that's what we in the germplasm bank business, we're all about. We want long-lived seed. So what are the questions that we're trying to ask? If we dry the air with drying beads, can we speed up the drying process? And will rapid drying have a detrimental effect on the seed viability? This is a question that has to be answered before you can scale out an implementation of a new technology like this. So our seed biologist postdoc said what we need to do is a controlled aging test. So our starting material was 21 seed accessions that we harvested from our Toluca station. It was about 35 kilograms in total. The initial moisture content of the seed was somewhere between 9 and 16%. Our protocol was very simple. We divided each seed accession in half, and we dried each half separately by our two different methods. One is our drying room with forced air, no heat, in El Batan station. And what we are comparing it to is using the Green Monster with drying beads, rapid drying in Agua Fria station. We keep track on how long it takes to reach the desired moisture content. And then we compare initial germination rates, and we do what's called a controlled aging test for each type of seed. And we compare their longevity curves. So what is a controlled aging test? It's a lab method that's used to speed up the process of seed aging. And how does it do it? You do it by manipulating two of the most important parameters that affect and influence seed longevity: relative humidity and temperature. And in this case, you expose the seed to 60% relative humidity, which is quite high, and 45 degrees Celsius, also high. So high heat, high humidity. You place the seeds in open storage in a hermetic box with a solution of lithium chloride at the bottom, which maintains this environment, microenvironment inside a growth chamber. And then you let it go, let the seed go, and at stages you start pulling seed from the experimental chamber, and you check the germination. You do germination testing. So what was the drying time in order to reach about 8% humidity? Well, in Agua Fria with rapid drying with beads, it took 4 days to reach that. In El Batan, in our equilibrium drying room, it took 21 days. So we checked the initial germination rates, and then we started to test and see if the longevity curves are the same. And here are the results. Wow, they're about as different as the same as possible. There are no differences in the seed longevity detected by the controlled age testing between these two kinds of drying. And this is a super, super important piece of information that we need to know before we can start telling breeding programs and other germplasm banks that they need to use dry beads. We need to show this. And this is the first time this has been shown. Very, very important piece of information. And these data are very fresh. The last data points were captured a week ago. So this was repeated twice, and we are confident to say that drying beads do not have long-term effect on long-term viability of seed. So just to give it the big context, the big picture, why is this important? It's important because it is now understood that 1/3 of the food produced in the world is lost before reaching the consumer. 1/3 is wasted. 4.5 billion people have aflatoxin in their food, and that's fungus growing in wet grain storage. And humidity is our problem here, and dry chain technology is the solution. So we believe that we have the data, we have the evidence that shows that this system will work, and it will work in rural communities in anywhere in the world, and it will work in any germplasm bank or breeding program seed storage. So that's the story of that project, and it still goes on. We're really interested in scaling out the use of drying beads, and we will continue to work in that area. In 2016, we had a genetic resources program meeting, and Kevin tasked us with he had a very special request to each scientist. And he gave us a series of I believe it was 5 different things. We had to stick to only 5 slides. One of those slides was, what is my one big objective? And this is in 2016. So this is what I went back, I took a look at it, and my objective was to pass on to the next curator of the CIMMYT maize collection the following. GRIN Global, which is the database system developed by the USDA and being used in international banks all over the world. We want that fully operational. We want a regeneration success rate of at least 75%. We want to have a complete set of CIMMYT maize lines, all available for distribution. We want no skeletons in the vault. We don't want backlogs of lots of material that could be useless, could be useful, but is not inventoried. So we don't want that. We want completely relabeled flasks in both vaults with functioning 2D barcodes. And we want a team with enough experience and dedication to be able to run the bank, even without a curator. So let's see if I reached that in 2020. So 4 years later, how do we do? GRIN Global Database, fully operational. This was fully met. All processes in our operations are linked to the GRIN Global Database. Regeneration success rate of at least 75%. Yay, fully met. In 2019, our success rate in our regeneration was 79%. Complete set of CMLs, all available for distribution. Not quite 100%, but we're getting close, 93%. 558 of the 604 CIMMYT maize lines are available for distribution. How about those skeletons? What about the backlog? Well, our total backlog has been reduced by 67%. In 2012, we had almost 8,000 bags of seed. And the sad thing is most of that was not inventoried. Okay. Over the course of the last, actually the 8 years, this has been reduced to 2,541 bags, which one might think seems like a lot. But what that is more active backlog. Those are, a lot of it is regenerations that are not quite completed. But the main thing is that 10-year-old seed, 20-year-old seed, that is all gone. And I want to give a little shout out to Martin Velasquez, who is actually retiring this week. And he is the one I credit for really, really getting a grip on this problem of backlog. And I congratulate him on great work. And the thing is although the number is still 2,541 bags, we have an inventory of what we know what we have. So do we have completely relabeled flasks in both vaults with functioning 2D barcodes? Well, we've got 1/3 of the way done. 9,162 of our 28,000 accessions now have QR barcodes, and this includes all the CMLs. This is what we called our relabeling function, and this was literally stopped by this COVID pandemic. So we were slowed down a lot, but it's an area that I hope Terry Molnar, who's my successor, will take on and really promote, because it's a very, very important thing. Knowledge is power, and if we don't know our inventory, we won't be able to use it, and the world won't be able to use it. Finally, do we have a team with enough experience and dedication to be able to run the bank, even without a curator? Well, I would say absolutely yes. But I believe it'd be a little bit boring without a curator around to spice things up. So also in 2016, we were asked, what is our proudest team contribution? And lo and behold, it actually is something to do with Guatemala. So in the Buena Milpa project, you saw how we are sharing our knowledge and technologies with communities in Guatemala. But we are also sharing our germplasm. And during 2016, our team prepared over, 785 maize accessions from Guatemala that had been lost by the national system there, and we repatriated them back. And this is a exercise of restoring what could be considered lost genetic diversity, and we are the only bank that could do it on this scale. So now we start thanking. Wow, my deepest gratitude is to the staff of the whole bank, and here's everybody, maize and wheat all together, one bank, and standing in front of our milpa garden, which some crazy maize curator thought would be a great idea to have right next to our bank. I want to thank our partners in dry chaining, Pedro and Kent from the University of California, Davis, Ariel Rivers, who was really a key person in the beginning of that project, Mario Fuentes and his team at Buena Milpa in Guatemala, Emerson Eggers, who works in distributing dry chain products through his relatively new company, Dry Chain America, Sergio Alonso and his team at Asakuch. We just couldn't do this without them. Rachel Cox was right there in the beginning, had a great idea in the Buena Milpa project, and now is doing wonderful work with her NGO called Earth Empower, and also as a provider of drying cards. And also Maria de los Angeles Merida, who is a curator at the Germplasm Bank and has been working with us. Thanks to our sponsors. Of course, the CG Gene Bank platform, once called the research program, but that entity is what provides us with our routine operations funding and salaries for everyone, including those who worked on these projects. The Crop Trust is the organization that manages our funding for routine operations and also holds our feet to the fire in terms of doing our job of providing quality seed. The USAID were the funders for the Buena Milpa project, and we also at the point where we had no money left, and we were at the last possible data collection point, and we were rescued by the CIMMYT CG Maize program, and that little last bit of funding got us over the hump and meant that we could complete that experiment. Along the way, I've had fantastic students, and this just illustrates some of our other projects, which I did not even mention. Denise McLean, who got her PhD working on the Morelos project. Then we have a project in Jala, and we've had two students, Luis and Armando and Aaron, who lived in Jala for 6 months and helped us collect data there with farmers. Vanessa Ocampo, who has just published a paper on her work and our work in Jala. Then we have a popcorn project I did not even mention. And here are some of the students, or most of the students that worked on that project. Natalia Almeida from Brazil. She was our very first, or my very first student intern, and launched us into popcorn. Also, I really want to thank my friend and colleague, who, whenever I think of the students, I always think of Carolina, because she and I have co-mentored many of the students in the bank. We've been on lots of driving trips together, going to a lot of different places in Mexico and Guatemala. And she's a maize lover, just like me. Also, last but not least, I want to thank the guy on the other side of the bank, Tom Payne, who really has been a great partner in running the bank. And also, I note here that in 2019, he won the Meyer Medal, which is one of the top awards in plant genetic resources. So he's been a great guy to work with, and we've had a lot of fun, but we've also done, I think, some really amazing things with our bank. And so now I move it on, moving back to my home in Ithaca, New York, where I'm going to get to know my little grandson, Ellis Baldwin. And he's an 8th generation New Yorker. And I'm quoting here our governor of the state, who says, even after having suffered probably one of the worst contagions of COVID-19, he says, "I have hope because I see evidence of better tomorrow." Thank you.
Wonderful. Thank you very much, Denise. Beautiful pictures and a nice story of some of the many activities that you have helped to lead and implement during your tenure at the bank. If you don't mind unsharing your screen, I'd like to just we had quite a number of questions, but we don't have much time. So I've taken the liberty of selecting a couple, and maybe you can easily read them if you, yeah, there we go. Let me share the screen. Maybe take a look at this first one, number 6. There were at least 8 or 10 and many people thanking you and congratulating you, but I thought, and most of the questions, frankly, were very specific technical details about the drying beads in particular. And so maybe just to encapsulate all of those, the one that I found most interesting is this trademark technology, or is it IP protected, or could we have farmers, and you showed an example of farmers trying to duplicate somehow, but how easily could we design our own or help farmers design their own drying bead technology? And then maybe move to the 2 questions on the screen.
Well, I think what we envision as the next step is to actually start implementing this on a larger scale in areas where there are community seed reserves and also networks of community seed reserves, and really start getting people familiar with how to use them. And I think it's very doable. It does require some investment in the beginning, but once you own those drying beads, they are basically indestructible. And the reactivation rate is much better than silica gel. Silica gel is another alternative, kind of a classic one. There's a number of advantages and disadvantages to drying beads versus silica gel. And in fact, the Kew Botanic Gardens use silica gel in their Blue Bins project, which is quite similar to some of the things we want to do. We're trying to convince them to switch to drying beads. So I think that it does require an investment in the beginning, but there are lots of different ways to use these drying beads, and people have been very creative and innovative with them in Asia, actually, where this technology began. I want to point out that this work that we're doing in the Americas, this is the first time that there's been implementation of these drying beads in the Americas. The issue was that there were really no published experiments results, and now we will be publishing our work very soon, and hopefully before the end of this year, and also other groups are starting to publish. So it's getting more accepted, and I think that there's a big future for this. I think it's going
to. Right. We need to go quickly answer to the next question. How can CIMMYT help establish and work with small community seed storage systems, and connect them to larger banks? What's our role in that, and how can we do it?
I think our role is basically exactly what we did in our work. talked to the farmers and looked at what we asked them what the problems were. We looked for a solution, and we implemented it, and so I believe that's basically scaling what we've already done here in this project.
Excellent. Thank you very much, Denise. I think we're almost out of time, but I don't want to let this opportunity go without presenting to you an official thanks. And really it comes with a lot of sentiment, I think, from colleagues, from myself. You've been working with us for 8 years. You've done a lot of very interesting projects, and you really only shared with us today in detail one of those. And I think you could have told equally or perhaps even more fascinating stories of the work in the state of Morelos, looking at in situ versus in the gene bank conservation of materials, the work in Hala, fascinating, the work with switchgrass collections in great partnership with INIFAP, also a wonderful example. But I suspect you chose this one because it's something that may have application and may be directly usable by many colleagues, including breeding programs of CIMMYT, who may want to extend the longevity of seed that they store of their breeding materials. So thank you for sharing this experience, and above all, thank you for sharing with us your expertise and your enthusiasm over these 8 years. And so as is more or less the tradition, we've prepared a plaque. Unfortunately, we can't hand it to you physically right now, and I'm not even sure how we're going to get it to you. But someday you should have this plaque in case you wish to hang it on your wall. And the plaque reads, CIMMYT recognizes and thanks Denise Costich, head of Maize Germplasm Collection from 2012 to 2020, for your dedication and contributions to CIMMYT's mission with excellence in collecting, conserving, safekeeping, multiplying, regenerating, and distributing maize germplasm, and for always working closely with smallholder farmers, which clearly has been one of your passions that you've emphasized during your tenure at the bank. You are a valued colleague and will always be an esteemed member of the CIMMYT family. So thank you very much, Denise, and congratulations, and really best wishes as you move back to meet your grandson, cute fellow in the picture, and to your next steps in your career and in your life. So congratulations and thank you. And I would invite everybody on the call, perhaps if you can, to switch on your videos. And even today, even if we were close to you, we would probably say namaste instead of the usual abrazo or hug. So namaste, thank you very much, and best wishes from all of us, Denise. Let me stop sharing so that everyone can also, if they wish, wave at you or say best wishes to you. Thanks, Denise. If you want to say any last word, go ahead. You have 1 minute. Otherwise, this is a great ending already to the seminar.
No, thanks, everybody. Thanks everybody for coming and sharing this. And I look forward to continue working. I'm not disappearing. I'm going to keep going. Yeah, I really look forward to continuing on with this work and other projects, which I didn't have time to describe. I could keep going for days, as you can see.
Yes, as we all know. Thank you. Thank you, Denise, and thank you, everyone. And have a wonderful day, evening, and retirement years to you, Denise. Thanks again. Bye, everyone.
Bye.
Thank you.
Thank you very much.